So what are the roles of alpha and beta here? We call it alpha beta pruning. What is alpha beta? Okay, so this is I have already explained a little bit here. So alpha represents the best value found so far along the path for max. Okay, basically along the from the root towards the from the leaf towards the root. So in that path, whatever be the current best value for max, that's stored in alpha. And beta represents the best value found so far along the path for mean. Along the path means from leaf towards the root. So for every node, we will have a value of alpha and beta. And if alpha is greater than or equal to beta, we will consider trimming the following paths. As the algorithm progresses, these values are updated. Okay, these values are continuously updated. If it is determined that current node cannot improve the outcome beyond alpha or beta, the branch is pruned immediately. Okay, so in practice, this can save a large amount of computation. Instead of searching the entire tree, the algorithm focuses only on the most promising branches. Only on the most promising branches. So in summary, alpha beta pruning is an optimization of the Minimax algorithm. It's an optimization of the Minimax algorithm. It reduces the number of nodes that must be evaluated while still guaranteeing the same decision as Minimax. By maintaining alpha and beta values and pruning subtrees that cannot influence the result, large portions of the search tree can be skipped, making the algorithm much more efficient. So now, I want to show you one thing, that how the move ordering is important. Okay, so what is the efficiency of alpha beta pruning depends greatly on the order in which the successor states are examined. Okay, so like here, initially min got 3, then it wanted to explore the other nodes. Fine, then I got a value of 2. Then when value of 3 here, then I come down here and check 2. And so this is already a pretty low value, which is lower than 3. So min will definitely choose this path when it knows that the earlier max was making his value 3 and I got a cheaper path. So if max comes this way, I will definitely play this move. Okay, so and then bring him down to 2. But if the most promising moves are examined first, more pruning opportunities are created. And conversely, if weaker moves are explored first, little or no pruning may occur. Like weaker move is like this 14 here. Okay, 14. If we explore 14, max will be so happy. So max will say that, okay, I want to explore the other. Then you find 5. Then you find 2, where min is happy. But because if the order was other way around, 2 was before, then 5, then 14, then you will probably not need to explore the other nodes. This is the first time it was necessary because we had to check if there was anything lower than this was possible. But here we already have a value of 3. So if we get a 2, I will stick with the 2 first. But because it was 14, I had to check 5 and the 2. This is important. For example, if the game tree illustrated earlier, it was observed that none of the successors of a certain node could be pruned because of the worst successor from min's perspective was generated first. Like worst successor was here. If instead of strongest success has been evaluated first, the other 2 would have been pruned. Okay, so for min, this is the strongest successor. So the other 2 could be pruned. For min, this is the worst successor. So the other 2 needed to be checked. As simple as that. This observation leads to the important insight. If the best moves can be examined early, alpha beta pruning becomes far more effective. But this is not possible in practice. You cannot know that which will be the best move among all the leaf nodes. But if it was possible, then alpha beta pruning can prune even more. If I know that, oh, this is best, this is 3, and there is nothing less than 3, so then I could have trimmed the other 2. So now, if considering the if best move would have been done, we can consider the impact on complexity. Okay, with good move ordering, alpha beta pruning reduces the number of nodes examined to approximately order of b to the power m over 2. B to the power m divided by 2. Okay, so like this, order of b to the power m divided by 2, perfect ordering. But that's the best case, where b is the branching factor and m is the depth of the tree. This is a dramatic improvement compared to Minimax, which requires b to the power m, if you remember. Now this is b to the power m over 2. This basically means square root of b to the power m. Like if earlier there were like 36, like let's say this is 36 b to the power m, and then this can be square root of b to the power m. So that means, let's say this is 36, so that will be 6 times 6 to the power 100 instead of 36 to the power or 35 to the power 100. So that will be much less. Okay, this will be possible to explore using, so the chess game can be explored using alpha beta pruning, the chess game tree. This is a dramatic improvement indeed. Okay, in practice this means that the effective branching factor is reduced from b to approximately square root of b. For a game like chess, the average branching factor is about 35. So with alpha beta pruning and good move ordering, the effective branching factor becomes about 6, as I said. Okay, that's much less. This allows a tree that are nearly twice as deep as though examined by plain Minimax to be explored. Like plain Minimax, let's say the or deep up to level 6 you could have explored all the nodes. Here you can explore up to depth 12. That means you are thinking of more moves, you are getting, so this is the difference between, it's said that this is the difference between a novice chess player and a grandmaster. So this is a huge difference. Okay, in the same computation time you can explore a bigger, deeper tree. When moves are explored in random order, so because you cannot always guarantee the best move at the beginning, so when moves are explored in random order rather than the best first, the number of nodes examined is about order of b to the power 3m by 4, 3m divided by 4, which is still a substantial improvement but not as powerful as the best case scenario. Okay, so best case scenario is best case if you get the best ordering of the leaf node, but in practice this hardly happens. Okay, so that brings us to the end of alpha beta search, alpha beta pruning, and then we will see some examples.